holes, which is just 1% of the nodes in the network, then you will have drop ratios, loss caused by the black holes of more than 90%. And if you consider that there will be some inherent loss due to collisions, due to route breaks, then this network will be down. So for the address-based intrusion response, we considered also the loss that is caused by black holes, but subject to the frequency with which misbehaving nodes change their addresses. So in fact, intrusion detection system will detect a misbehaving node, and after a certain time this misbehaving node will change the address, and if you exclude a misbehaving node based on its address, then you can circumvent the countermeasures. So what we can see is that for low frequencies, so for static addresses, the address-based intrusion response works quite well. If you start changing the addresses, then the loss will increase and the effects of the address-based intrusion response will decrease. This is quite straightforward, and in fact this is a quite simple approach to circumvent address-based strategies. So you can have some more sophisticated ones by saying, okay, if I do not receive as a misbehaving node, if I do not receive data for some amount of time, I will change my address. So you can even improve this effect from the perspective of the misbehaving node. So for the location-based approach, we evaluated the loss that is caused by black holes subject to the quarantine time. This means the time during which one quarantined area is active. And clearly, if we choose this too short, we will have a bad effect on loss, so we will have quite high loss rates. If we optimize this, and in this case the optimum is that, so for the scenario given here, the optimum is about 300 seconds quarantine time, then we will have loss ratios that clearly outperform the results from the address-based response. If we are confronted with misbehaving nodes changing addresses, yes please. Pardon? Mobility model is a random waypoint model. No pause time. It's between 1 and 2 meters per second. So it's a pedestrian scenario. And in fact, we split up, because if you use a random waypoint model, which is kind of a worst case model regarding mobility, if you have more predictable scenarios, then we'll be able to optimize countermeasures, something like wireless networks for cars, for example, vehicular ad hoc networks. Anyway, to reduce unwanted effects of this random waypoint model, because when you use random waypoint model, the nodes tend to go to the center, and we split up the simulation time. So we used simulation time, and we had several runs. So this 1 hour is split up into several runs consisting of some 5 or 10 minutes, just to limit the negative effects of these random waypoint model. Okay. So other questions on this? So the second point we have to consider is the loss caused by intrusion response. And we charge packet loss to the intrusion response from the time misbehavior is detected until it takes to inform the source and to stop sending data. So it takes some time. When the intrusion is detected, there is an error message sent back, and during the time this error message travels to the source will still be sending data, and this data will be dropped, and we charge this to the intrusion response and not to the misbehavior anymore. So for the address-based intrusion response, this loss is quite low because we just exclude one singular point from the network, just one node. If we consider the location-based approach, this is clearly a drawback of the location-based approach because we do not exclude one singular point from the network, but exclude a certain area from the network. So we also exclude nodes that are located in proximity to a misbehaving node, but are well-behaving, so could be used for routing. So this is clearly a drawback which we addressed in further work, and I will come back to this later. So this is the overall loss. Just to give the comparison, you can see that the curve of a defenseless network is raised by some 10% compared to the black hole loss. This is due to inherent loss, and here you will see that we are far above 90% for 10 misbehaving nodes and nothing will happen anymore on this network. So also for the address-based response, the results we saw from the last slide are raised due to inherent network loss. But what we can see is that although we have higher loss for the address-based, for the location-based approach than for the address-based approach, due to the intrusion response mechanism itself, we're able to have a lower overall loss for the location-based approach than for the address-based response. Still, loss rates of some 35% in a black hole case are not tolerable, and I will come back to how to improve this on a later slide. So I said we wanted to have two viewpoints on the problem. So the analytical model for mobile ad hoc networks is in fact a quite simple model that is easy to understand. And if you read the paper, you will say, okay, yeah, I agree to this. The model is based on probabilistic approaches combined with geometry. So for example, for the effects of the black hole attack, what we describe is the probability for the black hole being in a closer ring regarding the ADV ring search than the destination. This means that if a black hole is located in the same or closer ring than the destination, the route request will reach the black hole will be able to answer and will attract the traffic. The black hole is further away than the destination with respect to the ring search, then the route request will just not reach the black hole, and the black hole will have no chance to get active. So I don't want to go into the math here, but in fact, these few formulas are the core of the description of this black hole attack. There is not much more on this. So the effects of the location-based intrusion response we also describe by a probabilistic approach combined with geometry. So what we describe here is the quarantined areas and the effect that we have when the black hole moves. So the old quarantined area is still active. The black hole moves, will be active again, will get detected again, and will have a new area of influence where it can get active. And if we can describe this area and the number of nodes that will be located within this area, we can describe the loss that is caused by location-based intrusion response, and we can describe the loss that can be caused by black holes when they move for a certain distance. And still, the model is quite simple. So what you can see here is, in fact, the core of the model, not much more around it. What I want to show before I come to my last slide is the comparison of the model predictions with the simulation results. So what you can see here, the curves, in fact, are the predictions that were made by the model, and the confidence bars, so the intervals here, are taken from the simulation studies from the previous slides. And you can see that even if we have a quite simple model and we use heuristics to approximate side effects on the edges of the network area, we have quite good matches with our analytical model and the simulation studies. And this could be a hint that this is what we can observe in real-world scenarios. So, to come to the end, if you don't want me to continue, just to wrap this up, we've seen that address-based intrusion response in mind is not the way that should be done. Location-based intrusion response seems promising, yet we have to do some improvements. We have, because well-behaving nodes, bang nodes that could be used for to establish the network are excluded when they are in proximity to misbehaving nodes. The question is, how can we improve this location-based approach? And we studied two approaches. And one is harnessing the delay tolerance of applications. So if you consider something like short message services or email, then the transmission could just be delayed if you are in a quarantined area until you leave this area, and this should be done transparent to the user. So for the emergency response scenarios, it's just something like it's better to deliver an emergency call some 20 seconds later than never at all. What we found is that we can recover the functionality of the network subject to the loss caused by black holes nearly completely, so we can have some good put in the network of near 100% if we are able, or if we are willing to take transmission delays that, for the scenario that I just showed you, may reach up to several minutes. Second approach, if we have some more constrained communication regarding time, is to use an adaptive transmission power of the nodes, and this is just to minimize the size of the quarantined areas. This means that if I'm located closer to a well-behaving node than to a misbehaving node,